Okay, so spring force and the gravity force talked about in the previous video. This time we're going to talk about our friction forces, and that will pretty much comprise the four forces that we can calculate. There is a fifth force I like to talk about in this kind of deal of this kind of part of the unit, and that's the normal force. So I'll go over that as well. But we can't really calculate the normal force. There's no equation for it. There's just some assumptions that we can make using Newton's first law, and you'll see what. Okay, so forces and friction. I said that our two types of forces exist for friction. We have our static friction, which I called our sticky friction, sticky flavor. And we also have a kinetic, which I called our slidey flavor. These have similar equations. They look very, very similar, but they vary in one key difference. Well, two key differences. Our static friction, really, it only exists in two cases. And that case is, first one is when there's no motion whatsoever. So you might remember, or you might have some experience pushing things and getting them sliding across the ground. And you'll notice that it takes a lot of effort to get it to start moving, more so than it does to keep it moving at a constant velocity. And there's a reason for that. Our static friction equation and our kinetic friction equation both have this thing that looks like a weird M, U, and amalgam of both letters, and that is the Greek letter mu. Looks like that. We sometimes give it a subscript. We'd say something like mu sub s for static, or mu sub k for kinetic friction. And this is an important quantity that we'll talk about in a moment. I just want to point out that static friction and kinetic friction are very different, but they come from the same interactions. So a static, or sorry, let's talk about kinetic friction first because it's kind of more intuitive, I think. Kinetic friction is has an equation. I will denote it as lowercase f sub k. That's just the notation I learned with. If you like to call it something else, that's fine. Capital F, whatever. But I just like the lowercase f. So lowercase f sub k, and again, there's a vector bar across the top, so this is a vector equation. F sub k is equal to mu sub k times the normal force vector. So the issue is the normal force vector points down, and the friction force vector points in a different direction. I'm not going to worry too much about that at this point, because it requires a little bit more work with some mathematics. But for now, let's just assume that this works out. For the scalar version, it makes a lot more sense, in my opinion. That is just F sub k scalar, so the magnitude of our friction force is equal to mu sub k times our normal force n. This is really what we're going to be working with for the most part. There might be a negative sign somewhere that we throw in to make sure that the direction is correct and that happens, but again, that's a free body diagram type of discussion, maybe a Newton's first, Newton's second law type of discussion, or Newton's third law too. All right, so if friction force happens, and this is how we can calculate it. But our friction force occurs because of a surface interaction. So when I have, let's say, a rough surface and a smooth surface that kind of come together. So here's my rough surface on the bottom, and here's my smooth surface on the top. When these things slide across each other, maybe this one's moving this way, and this one's moving this way, or one of them's moving, the other one's stationary. Doesn't really matter. That's a reference frame thing. What happens is there's some small microscopic interactions, and this mu sub k thing, which we call the coefficient of friction, this mu sub k thing takes our normal force magnitude and scales it to be the size of our friction force. And this mu sub k thing, the coefficient of friction, really depends on the surfaces that are interacting. You might think, okay, well, if I take two pieces of sandpaper and I rub them together, that will have a higher coefficient of friction than maybe two pieces of metal or two pieces of glass rubbing together. And you'd be wrong, which is weird because you think they're really rough and rough things are harder to scrape across, and you're correct, but there's also some other interactions that can happen between molecules and like these. When we start dealing with like silicates and we start dealing with metals, they have these weird orbitals that happen. And they can overlap each other very easily, and you can form these temporary or even permanent bonds that we call cold welding for metal. And I'm not sure what the interaction is called when you do it with glasses, but still, there's some sort of interaction between the electrons in these molecules, and it causes a huge, huge friction force. Well, not huge, but bigger than you'd expect it to be given how smooth these surfaces are. So when we slide metal across metal, we have to lubricate it. Something like oil. That's why we put oil in our car engines. But the mu sub k value, if it gets bigger, it means that there's more friction. So something like your tires, so like rubber, oop, ugly R. So this one, rubber on asphalt, it has a kinetic friction coefficient of usually around 0.8 to 0.9. And then labeled as kinetic. And then our static coefficient is going to be somewhere around 1.0 to 1.2. Again, depending on what table you consult, it'll be some range, somewhere in that range. We could do something like metal on metal. So metal and metal. I'm looking up the one for aluminum. It's something like 0.6 and 0.6 for both, like 0.58 or something for the kinetic and like 0.6, 0.61 for static, but still it's really close to 0.6. So these things really depend on the surface interactions that happen and whether it's like a rough surface interaction where it's like a big thing, very clearly rough, or whether it's these very small electronic interactions, the electron orbitals of the surfaces. Doesn't really matter. This mu k thing does a good job at encapsulating every effect that could possibly happen. So mu sub k is really, really important for us to know for a lot of surfaces. And there are tons and tons of tables out there. You can go like engineeringtoolbox.com, look up a huge, huge list of them, and just go crazy calculating friction. That's what you do. That's certainly what I will be doing this weekend. All right. If we want to calculate a kinetic friction force, let's say I have a surface with the mu value of 0.1. So this would be a very low friction surface, maybe like an air hockey table with the air jets going and the plastic puck on it, or maybe something like ice in an ice skate. A very low coefficient of friction. And then let's just say that our normal force is 30 newtons. So if I plug those into my calculator, I will get 3.0 newtons. There's no units on our mu sub k value. Mu sub k's do not have units, and they are scalars as well, so they are always positive. So when we do these type of problems, we have to be careful about our direction for sure, but we also have to know that anytime we calculate a mu value from experimental evidence or something like that, and we collect our data and we go through and we do our calculation, or maybe we do our plots or whatever, whenever we calculate something like this, we need to be sure we need to be sure that this value we get is positive and has no units, because my newtons come from my normal force, right? N. N is a force. N normal force has a unit of newtons. And the friction force is a force, so it also has units of newtons. If mu has any units other than nothing or newtons per newton, which is nothing, 1, I guess, then it will cause different units, and we will not have a friction force. Maybe if we had 0.1 meters times this force, we'd have a friction energy, but that wouldn't be a force. It has to be unitless and positive. So mu sub k, mu sub s, well, mu sub k and mu sub s, these mu values are coefficients of friction. They are positive, upbeat, and outgoing. Sorry, they are positive and they have no units, or what we call unitless. All right, so there's our friction force. We calculated it, 3 newtons. Everybody's good. We're done. This doesn't tell us about the direction. Again, direction comes from free body diagrams and from careful analysis of the physical situation. That is a future conversation we'll have. Let's go ahead and try to do a little bit different one. Let's say I'm calculating my friction force. So I pull something along at a constant velocity, and I measure the force while I'm pulling it at that constant velocity. And I measure a force value of 15 newtons. So I pulled this object, across a table, and I measured the value of this horizontal force, and it was 15 newtons. And I know that the force I measured is the same as the friction force. Why? Well, we'll talk about that again, Newton's first and second law. Friction force is 15 newtons measured by a force probe or Newton meter or something. And then we also know what our normal force is. Say we measured our normal force with our magical normal force measurer device. We haven't really talked about what the normal force is, but we will. Normal force is 30 meters, or 30 newtons. So I set up my equations. Friction force, kinetic, is equal to mu sub k, the kinetic coefficient of friction, times our normal force. But I want to know what my kinetic coefficient is, because that's maybe my experimental goal. So I calculate mu sub k. To do that, I would have to divide both sides by that normal force. Go. Divide by normal force, I get friction divided by normal is equal to mu sub k. And then I can just take my friction force of 15 newtons, divide it by my 30 newton normal force, and I would get a value of 1/2 or 0.5, and I will not have units. Because when I divide my newton on top, it cancels out the newton on bottom. So my coefficient of friction here is 1/2. Okay, let's take a break for a moment talking about forces that we can directly calculate. And let's talk about this N force. What is this N force and what is a normal anyways? Well, normal is kind of maybe hard to define in terms of social stuff, but normal in physics and mathematics is fairly easy to define. When we say something is normal, we say it is perpendicular, or is the same thing as saying it is perpendicular. We call this thing the normal force because it acts perpendicular to the surface. I have a surface here, maybe it's a tabletop or something, and I set a box on top of that tabletop. There's some surface interaction down here that could cause friction if I were to push on it, but let's not worry about the push part so much. Let's think about the gravity part. If I have a force of gravity pointed downwards, I would see an object accelerate downwards unless there is a counter force to balance it out. So there is some force that exerts upwards from the surface due to this interaction, and it cancels out the force of gravity, so that when I add my force of gravity plus my normal force, they're vectors, I should get 0. And that thing is a 0 vector. It's an important thing for math, but it's not so much for us. Just think of it as being a. So if I add these two vectors together, maybe using like a tip to tail method, I should get 0 out, which means that my acceleration would also be 0 and my velocity would stay the same. So if I don't move this thing at all, I will have 0 velocity initially. And if it's on top of a table, like on a horizontal surface, then I will have a normal force equal to my force of gravity. And I can tell that because it doesn't accelerate up or down. If it started to spontaneously gain velocity, pointed upwards or pointed downwards, that would be kind of weird, right? And so we have to maybe make this assumption that the normal force is equal to the force of gravity. However, there's one very, very big caveat, and that is this only works for horizontal surfaces. Once we get further into Newton's laws, we will talk about how the normal force can be affected by things like inclined planes and adding mass to stuff and how that affects our friction force as a result. But for now, we're just going to work in the horizontal surface type of world, and it's going to work out very nicely for us. So back to our normal force. If I want to calculate what my normal force is on a horizontal surface with no additional mass added to it, I could say that my normal force is equal to the force of gravity. And we know the equation for the force of gravity from the previous video is mg. So my normal force, magnitude, is equal to mg. So this does not have a direction to it. We have to insert the direction later once we know what direction it's going to point. But for now, we can calculate the value of it, how much force it is, how many newtons it is, using normal force is equal to mg for a horizontal surface with no additional mass only. Reason why I want to talk about this normal force for, in this part of the conversation is simply because it affects the friction force. And if I want to calculate a friction force, I need to be able to figure out where my normal force is, what direction it points, and how big it is. So back to our friction world, we'll talk about kinetic friction one more time. We know the equation is F sub k is equal to mu sub k, the coefficient of kinetic friction, times our normal force. If I use that relationship from the previous slide, I can say that my force of friction is equal to mu sub k times mass times the gravitational acceleration constant, 10 meters per second squared. This I can now use to directly calculate what my friction force is if I am on a horizontal surface. And, and with no additional mass. Adding mass and adding an angle of incline will both change. They'll either reduce or increase our friction force, depending on what's happening in our physical situation. Okay, so now we have this new equation that says friction force is equal to mu k times mg. Let's say I know that my mu k value is 0.25, kind of a oiled wood on wood surface, something like that. 0.25, so it's kind of slick, but not as slick as say ice in an ice skate. 0.25 is our mu sub k value. Maybe we have a mass of wood that's 1 kilogram. We want to know what is friction force. We can calculate it saying friction force is equal to mu sub k, which is at 0.25, unitless, times m, 1.0 kilograms, times g, 10 meters per second squared. Units I get out are kilograms times meters per second squared. That's what we call the newtons, so that's good. And doing this dimensional analysis, I don't want to stop the flow, but this is a really important topic. Doing this dimensional analysis will really help you out checking and finding problems. If you accidentally made a mistake or something and you get something weird, like an energy that's in kilograms or a mass that's in like Webers or amperes or something, then you have a problem with your calculation. You should probably go back and double check it. So it's a really good test to see if you're doing the correct thing. Anyways, I will have this friction force. I will get units of newtons out because I get kilograms times meters per second squared. All that is left to do now is plug some stuff into a calculator. The result I get is my friction force, Fk, is equal to 2.5 kilograms times meters per second squared, or 2.5. Do one more with our friction or kinetic friction stuff, and then we'll go on to static friction. So kinetic friction, maybe I measured this friction force, F sub k, and I got 100 newtons out. I also can measure mass pretty easily. I can put it on a balance or a scale, and I can figure out that my mass was 2.5 kilograms. I want to calculate my coefficient of friction for my 2.5 kilogram mass in my tabletop. So I go ahead and I set up my equation, which says my friction force, F sub k, is equal to mu k times my normal force. I know that my normal force, because this is a horizontal surface and I didn't add any mass to my wood block, or I would get mu sub k times mg is the same thing as mu sub k times n. Now I can calculate what my friction force is. So friction force, or calculate, I know what my friction force is. Now I can go about calculating my coefficient of friction. I'm going to divide both sides by mg because I want to isolate that kinetic friction coefficient. Those cancel out, and what I'm left with is on my left side, I will get mu sub k, and that will be equal to my friction force divided by mass, and also divided by the gravitational acceleration constant. That would be 100 newtons for my force of friction, 2.5 kilograms for my mass, and then 10 meters per second squared. Plug that into my calculator, and I will get somewhere around 4. And this was just a demonstrative example, because usually our mu sub k values are not that big. Our mu sub k values, and just one more last bit about mu sub k and mu sub s values, these usually are between between about 0.01, maybe something very, 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 very low friction, between 0.01 less than or equal to mu, less than or equal to 1.0. There are exceptions to the rule. I don't know of any negative mu values. I don't think that would happen because it's saying that your friction is so great that, or so small, that if you push on it, it helps you push. So having a negative mu value probably not going to happen. Having a 0 mu value is like the ideal no friction situation, so also not physically possible. But there's also ones that are bigger than 1. Some of the ones that come to mind are rubber, asphalt. We use these for that way for a reason, right? That's a reason why rubber is used for our tires and why asphalt is used for our roads. Because that coefficient of friction is so big, or at least the static coefficient of friction is so big, it helps us a lot getting traction. And if we have snow on the ground, it helps us. It's just a good idea to have lots of friction between your tires and the ground, because otherwise you slide, and that's not good. Okay, mu sub k, also mu sub s, this is true for both of them, are between 0.01, very, very rarely is it that small, and about 1.0. Sometimes the biggest I've ever seen was about 1.2, and that was, again, like a special rubber on a special asphalt that nobody uses in real life. Okay, last force to talk about. This will be our static friction force. I said that the static friction and the kinetic friction forces look very similar in their equations, and I'll just go ahead and write out what our kinetic friction is again, just so you can remember it. mg, that's true, u sub k times n. And I will also put next to it our friction static force. The big differences that you might notice so far are that one has a mu k for kinetic friction coefficient, and one has a mu s for static friction coefficient. I also didn't put an equal sign between F sub s and mu sub s times n. The reason why is because it's not equal to that. It is less than or equal to that. So if mu sub s times n is what we would call our maximum static friction force. So F sub s max is equal to mu sub s times n. This is really important because if I exert a force on an object, we'll draw a little diagram here. I exert a push force, F push, in this direction. An F push that I exert is less than the maximum static friction. If that were to happen, it's kind of like you pushing on a really solid rock or something that's really heavy. You just can't move it no matter how hard you push. That's because the static friction of it is much bigger. Well, the maximum static friction is much bigger than your push force. But if this were a free body diagram, we'd have a weird thing happening where I push in this direction, but my acceleration is in this direction. And that's not what happens when you push on a rock that's too heavy for you to move. What happens is that your acceleration vector should be 0, right? It doesn't move. It doesn't start accelerating over you, unless there's like gravity at play or something like that. It just stays put. So when we have a push force that is less than the maximum static friction force, our friction force exerted back is only up to the push force. So the thing about friction force or static friction force is that static friction it will only be as large as it needs to be. Cancel out another force. It will not be bigger than that. If it is bigger than that, then you see acceleration. But again, if it's too heavy for you to push, it doesn't move. So in this case, I've said we push on something big and heavy, it pushed back on us, and overall the total, if we add our vectors tail to tail or tip to tail, we should see no resulting force, no net force. That would be a situation where we have what we call balanced forces, because one force is equal to the other force, they're pointing in opposite directions, and so they cancel each other out. Static friction also has a maximum. If I exceed that maximum, then some stuff happens and I start to accelerate. But the maximum value of static friction, maximus, the maximum value um, is mu sub s times n. One more thing, I know I kind of keep breaking up this talk about mu sub s, maybe I should do it all at once, but one more thing about mu is that our mu sub s value for two surfaces is almost always larger than our mu sub k value. Going back to the point that I made, when it's harder to get something started moving than it is to keep it moving, that's because mu sub s is bigger than mu sub k, and so F sub s also gets bigger than mu sub k, because our normal force only depends on gravity and the interaction between gravity pulling it down and the table or whatever surface pushing it back up. So mu sub s is bigger than mu sub k. That causes friction static to be bigger than our kinetic friction force. Do an example or two. These are very, very similar to the type of problems that you would do for a kinetic friction type of example. But the only difference is that when we talk about friction force, when we actually use this equation, F sub s is less than or equal to mu sub s times n. If we're going to use this equation, we can't really use the less than part. We don't know what it is. We'd have to use Newton's second law to figure out what our value is. So there's been a couple questions that I've given on exams in the past, and some of them are like, your maximum static friction, F sub s max, is equal to 5,000 newtons. You exert a push force on the object of 5 newtons. What is the resulting static friction force from that push force? And people will often answer things like 5,000 newtons or negative 5,000 newtons. Maybe. Sometimes they'll think, I got to really, really buckle down and do some math here, and they'll take 5,000 newtons and they'll subtract 5 newtons from it, and they'll get 4,995 newtons. These are all incorrect. The reason why is because F sub s is less than or equal to mu sub s times n. This would be equal to, that would be our maximum. This would be something slightly less than our maximum. That would be our net force magnitude. But what's really going on is that our friction force will be equal to that push force. So if you just notice that, all you have to do is say push force. So that means that our friction force is 5 newtons, but in the opposite direction. So that happens, quite a bit. So be aware of that. If you were given a force that is less than the static friction force's maximum, static friction force will only exert the same amount back. The only other way that we can really directly measure the non-maximum static friction force is through Newton's first law, right? And again, another topic, another day. So let's do a couple calculations. So sometimes when you're given these problems for static friction, you'll be told something like the force probe has a maximum, or the force probe has a spike here, and then it drops down, or something like that. But the point that they're trying to tell you is that they're giving you F sub s max. And if they're giving you that, you can use this equality and do some problem solving. F sub s max is equal to u sub s times n. Again, we're on a horizontal surface for this part of our discussion, and so mu sub s times n becomes mu sub s times mg. Like I said before, our force of gravity is equal to the normal force because we are currently on a horizontal surface with no additional mass. So if I have a block of wood with a mass of 10 kilograms, and I have a friction coefficient, mu sub s, equal to 0.70, and I want to calculate the friction force, or the maximum friction force, I would just use my equation that says mu sub s times mg, plug in my mu sub s value of 0.7. Again, that's unitless and positive. Plug in my mass, 10 kilograms, plug in g, 10 meters per second squared. And if I plug this in the calculator, I should get somewhere around 70. Looking at that, just kind of quick math, I take 10 times 10, that's 100. 10 times 100 times 0.7, 70. So 70 newtons is our maximum static friction force. What if I were to push on this with 45 newtons? Well, I would get 45 newtons of force back. Push on it with 50 newtons, I get 50 newtons back. If I push on it with 60 newtons, I get 60 newtons back, 65, 70 newtons I push on it, I'll get 70 newtons back. If I push with a force of 70.00000000001 newtons, I will get motion, and quite a bit of it. Because my mu sub s value is bigger than mu sub k, and when I overcome that maximum static friction, I enter into the kinetic friction regime when it starts to slide. That means my F sub k value, the maximum kinetic friction, will be less than my static friction. And so all of a sudden, all this force will drop out from the friction. It'll decrease dramatically, and we will see acceleration. The block will start to slide. Okay, I think that's about it for our friction force, our static friction, kinetic friction, normal force. In the previous video, we talked about gravity force, and we also talked about the Hooke's law spring force or elastic force. So just to really recap, summarize everything that we covered in these two videos, we had a force of gravity, Fg. We calculate that using the formula mg. Again, these are scalar quantities, so I'm not doing anything fancy. We have a spring force or an elastic force that's equal to minus k times delta x. We have a static friction force, which is less than or equal to mu sub s times our normal force. A kinetic friction force, which is equal to mu sub k times our normal force. And we also have this relationship that says for horizontal surfaces with no additional mass. So, oh, that's a weird way of spelling horizontal. For horizontal surfaces with no additional mass, we get normal force is equal to Fg, which is equal to mg. Again, Fg is the force of gravity, mg is mass times. You'll see in the future that this mg thing actually comes from Newton's second law. And where that comes from, kind of an interesting thing. But we'll get to that when we get to it. Otherwise, I think we're about done here. This covers our forces. This allows us to calculate what each of these forces are. And then once we talk about Newton's laws, we can then take those forces that we can calculate, relate them to forces that we can't calculate, like tension forces, pull, push forces, all kinds of other forces. We can relate them to them through Newton's first, second, third laws, and we can solve for them as well by saying that our force of gravity is equal to our normal force. So we can calculate normal force. Our friction force is equal to our push force. So we can calculate our push force. Stuff like that. But until then, good luck, and I hope to see you soon.